Hi everyone, I'm Eric and I work at Intel as a cloud software engineer. I'm going to show you how to easily switch between running an AI inference workload on OpenShift using an Intel CPU to using an Intel GPU. First, let me tell you about the Intel Data Center GPU Flex series. There is the Intel Flex 140 and the Intel Flex 170 card. The Intel Flex 140 has 2 GPUs per card with 8 Xe cores per GPU for a total of 16 Xe cores for computation. It is half height, so it can fit in tighter spaces. There's a maximum memory capacity of 12 gigabytes. The Intel Flex 170 is a single GPU, but it has 32 Xe cores for that GPU. It's a full height card with twice as many Xe cores that use twice the power of the Flex 140 series. Its maximum memory can go up to 16 gigabytes. Both of these cards are intended for data centers to run cloud workloads or to be used at the edge. Now there are 6 different types of workloads these cards are ideally suited to run. The first is simulation and visualization. GPUs are really great at parallel number crunching. The second use case is machine learning and also AI inference. Later in this video, I will show how to run AI inference object detection workloads on OpenShift using our Intel GPU plugin. The third use case these cards are ideal for is transcoding and gaming. The Flex series supports the newest royalty-free AV1 codec for hardware encoding, decoding, and transcoding. AV1 is the open source codec that rivals HEVC or H.265. The Flex 140 has 4 media engines for transcoding, whereas the Flex 170 has 2. Content creation is another workload that the Flex series of cards can accelerate. There is also the virtual desktop infrastructure as a workload. Finally, there is cloud gaming acceleration, which could be on Windows or Android. One of the nice features of the Intel Data Center GPU Flex series is that each GPU has up to 31 virtual functions. The Flex 170 can support 31 virtual functions, and Flex 140 supports 62. There is no additional cost to enabling and using these virtual functions. For the AI inference being shown later, I am using OpenVINO, which is an open source deep learning toolkit developed by Intel. It helps accelerate development of high performance deep learning, inference, and computer vision in applications used from the edge to the cloud. Many different machine learning platforms are supported. The widely popular TensorFlow is supported, as is PyTorch. Intel releases its own highly optimized distribution of PyTorch that has AVX512 and AMX CPU acceleration, as well as Intel Xe Matrix Extensions AI engine for GPU acceleration. Caffe Onyx are supported, as well as MXNet and Keras. The nice thing about OpenVINO is it abstracts the hardware layer away. With just a simple 1-letter change, you can change from running AI inference on the CPU to running it on a GPU. I will show you how to do that later. VPUs and FPGAs are supported by OpenVINO as well. Intel provides an OpenVINO operator that is certified for OpenShift and is integrated to work with Red Hat OpenShift Data Science, which is also called Rhodes. When you install it through Rhodes, there is integration between OpenVINO and the Jupyter notebooks. To expose Intel accelerators in Kubernetes and by extension OpenShift, Intel has created a device plugins for each accelerator. The plugins use the device plugin framework for Kubernetes, which tracks numeric resources that can be assigned to pods. To make it easy to install these plugins in OpenShift, Intel works with Red Hat to certify an Intel device plugins operator to manage the lifecycle of the device plugins. Each plugin then gets validated and certified on OpenShift. The picture on the left shows the certified device plugin operator. The GPU plugin works with both integrated and discrete GPUs. An entire GPU can be dedicated to a container, or a GPU can be shared among containers as long as the shared dev num flag is greater than 1. This setting dictates how many containers can share a single GPU. This allows flexibility to share a GPU among less compute-intensive workloads or to dedicate a GPU to more intensive workloads. There is also a device plugin for Intel's software guard extensions, also known as Intel SGX. This is a set of security-related CPU instructions that allow user-level software applications to store data in an encrypted memory enclave. There is support for attestation to ensure the enclave is legitimate and not tampered with. A good use case for Intel's SGX is storing the private keys for assigning certificates. Finally, there is the Intel Quick Assist technology plugin. This can be used to accelerate cryptography or compression decompression. The Quick Assist plugin uses VFIO and virtual functions to assign and isolate resources. All of the device plugins are managed by a single Red Hat certified device plugins operator. It allows per device resource definitions using CRDs or custom resource definitions. They are not being used to manage the driver lifecycle. For the demo I'm showing later, I'm using an out-of-tree GPU driver as it has not been fully integrated into Red Hat CoreOS yet as an in-tree driver. To install the driver, the Red Hat Certified Kernel Module Management Operator was used. I'll show you what that looks like later. The Intel Device Plugins operator is in the Red Hat Ecosystem Catalog. If you're using regular Kubernetes, you can install the device plugin operator from operatorhub.io. This is a public registry for Kubernetes operators. It includes many different operators from the community, including the Intel Device Plugins operator. The Intel Device Plugins operator has a lot of additional device plugins beyond just GPU, SGX, and Quick Assist. If you look at the picture on the right, you can see how the GPU plugin can be configured. You need to have a Red Hat certified node feature discovery operator installed within your cluster to label all of the node capabilities. The plugin uses Node Selector to ensure that it only runs on nodes where a GPU is found. Now let me describe what my demo setup looks like. I am using my own bare metal cluster on user-provisioned infrastructure. I am using a Jupyter notebook that is part of the OpenVINO examples. One of those is showing how to do object detection. In this, I set the compiled model device name to be CPU. I run that bit of code to compile the model and then schedule to run on the CPU. OpenVINO will use libraries optimized for CPUs to do the inference. The object is then detected. I'll then show that the CPU spiked just a bit when it did that inference, but the GPU did not. I'll then take the same notebook, change the CPU to GPU, and recompile and rerun the model. Now let me show you my demo. Here is the OpenShift console for my cluster. It's currently running version 4.12.6. If I go to my operators, you can see I already have some installed. If you were to set this up yourself right now, you would need to install the GPU driver to the supported nodes. Currently, the GPU driver is out of tree, which means it needs to be installed using the kernel module management operator. The driver will be integrated into the OS in the future, but for now, you need to use KMM. I already have this GPU driver module installed. If I go to my compute node and click on my GPU node and then click on the YAML, you can see the details of the node as Kubernetes labels. On row 47, this node is labeled with GPU:true. Both the GPU driver and GPU plugin use the GPU:true label to know to run on this node. All of these labels were automatically added from the node feature discovery operator, which you may have noticed when I first scrolled past the KMM. This specific worker node has an Intel Data Center GPU Flex Series 140, which I'll be showing the demo on shortly. Let me go back to the operators and click on the Certified Intel Device Plugins operator. If I click on it, you'll see there is a GPU device plugin instance already running. I'll click to create another instance so you can see what options are available. However, I don't need a second instance, as this instance will run on every node with the GPU label set to true. Now, if I go back to my installed operators, you'll notice there is already the Red Hat OpenShift Data Science installed operator with an OpenVINO toolkit operator. Within Rhodes, there are other applications that get installed like Jupyter Notebooks. When the OpenVINO toolkit image is selected from Rhodes, it comes with CPU acceleration support, and more recently is being updated with GPU offloading. Now, if I go back to the OpenVINO operator, I can show you one of these Jupyter Notebooks. I already have one created, so I'll just start from there. If you were to click the Create Notebook, you would create an instance which would create a new notebook, including all of the OpenVINO binaries and sample models to try out. Let's actually go to one of these running notebooks and look at its details. I will use the search, change my project to all projects, and search for the notebook. If I click on the details and go into the YAML file, I can go to the resources and requests. There you'll notice I requested a notebook with one gpu.intel.com/i915 resource. This request, along with the GPU plugin, made sure that this notebook ran as a pod on that GPU node. Now let's open up the Jupyter Notebook. Under Networking, Routes, I can search for Rhodes to get to the Rhodes interface. Since I already have this set up, I have an OpenVINO Jupyter Notebook server spawned already. I just need to access the notebook server. This will open up my already running Jupyter Notebook. There is a Demo GPU and Demo CPU tab with the exact same inference demo with only one little change between them. If I scroll through the sample code, the first thing done is to import Python libraries in addition to others. For this demo, I'm using an existing OpenVINO sample object detection model that has already been trained. First, we need to download the model in the code and convert it. This is to get into the OpenVINO IR format. Then we load the model. If you look at the screen, you'll see device name equals CPU. That is telling OpenVINO to use CPU acceleration to do the inference. This step will compile the model to be used shortly. Next, we have a lot of code to process the model with some existing object detection classes like person, bicycle, car, etc. If I keep scrolling down, there is some more code to run the live object detection. Before I run it, let me get the Grafana charts loaded so you can see the CPU and GPU utilization. I'm going to go through the networking routes and search for Grafana. Once Grafana is loaded, I just need to click on the CPU and GPU utilization dashboard that I have already created. To scrape GPU metrics, you can use XPU Manager from Intel. There are some reference Prometheus and Grafana YAML files that can be tweaked and integrated into OpenShift. As I click around, you can see the CPU utilization is very low right now in the system. The GPU utilization is currently at 0. You might notice that there are 2 GPU utilization gauges. That is because this is an Intel Data Center GPU Flex 140 card, which has 2 GPU units. Now let's switch back to the Jupyter Notebook and run the CPU inference. This is a sample OpenVINO video that I'm running for a total of 30 seconds of inference. You can see the person is being detected with the red box as they walk through the frame. If you wait just a moment, you'll see on the left side a car drives up and is recognized as a car eventually. This is due to the model and not because of this CPU. If I switch back to the Grafana, there's a bit of a delay from the CPU usage actually being shown. Now if I switch back, the inference is still running. You can see that the CPU utilization is really starting to climb. There's at least a 5-second delay from when Grafana updates and a bit more delay to actually scrape the metrics and output to Grafana. You'll notice the GPU utilization is still 0 on both GPU units. Looking back at the inference running, it is about to finish. Now that it is finished, I'm going to flip back to Grafana and you'll see that the CPU utilization shown is already starting to drop. Now let me repeat the exact same thing but run with GPU inference. If I go back to the load the model section, it is only a single letter change from C to G to have the workload run on the GPU instance. Let's scroll all the way down to the bottom and run the same inference again, but this time on the GPU. Like the other video, this one will run for 30 seconds. What is happening behind the scenes is that the Jupyter Notebook has one gpu.intel.com resource available in the pod. As I look at the GPU utilization, you see that the yellow line has started to climb to 100%. The green line is still at 0%. All of the inference is running on one of the GPUs on this Flex series GPU card. If you recall, each GPU on the Intel Data Center GPU Flex Series 140 has 2 GPUs, each with 8 Xe cores. The other Intel Flex Series 170 has 1 GPU, but with 32 Xe cores. The inference continues to run. The CPU utilization has dropped significantly while the job runs on the GPU. That was an example of how easy it was to use Red Hat OpenShift Data Science and Intel Certified Device Plugins and OpenVINO to accelerate AI on the CPU or accelerate AI on the GPU. With OpenVINO, it literally was just a single letter change from C to G to change where the workload was run. I posted some links to our GitHub for our Intel device plugin OpenShift operator and driver. The out-of-tree driver is just a temporary solution until the GPU driver is integrated and in tree. In addition, our Intel device plugins for Kubernetes has the source code, YAMLs, and customized for all the plugins for Kubernetes. Thank you for watching.